Alright, so we're going to talk about the relationship between electric fields and electric potentials. An electric field is present around any charge, whether it's positive or negative. That field around the charge will exert a force on any other charged object within that field. We represent these electric fields with something called field lines. These field lines will point towards a negative charge and away from positive charges. The density of the lines will tell us how strong a charge is. So if we look here, this negative charge on the right has a lot more lines pointing towards it than this negative charge here in the middle, telling us that this negative charge is a lot stronger than this one. And likewise here on the left, we see again that the lines are pointing away from a positive charge. So lines away from positive towards negative, and dense lines equals a stronger charge. Now, the force of two electric fields will interact with each other a lot like the gravitational force of two objects will. So here in this case, we see the Earth and the Moon. Their gravitational forces and fields will interact with each other. And similarly there on the bottom, we can see that two charges are going to interact with each other as well. Their fields will interact with each other. The difference being that electric fields depend on the strength of the charges, and gravitational fields depend on the mass of the objects. Electric potential will tell us how much work you can get out of an object positioned at a specific place relative to a point charge. Similar to gravitational potential energy, electric potential energy depends on the magnitude of the charges of two objects and the distance between them. So if we look at this example here on the left we're looking at gravitational potential energy, and we know that if we go from the first floor up to the fifth floor, our height's going to increase and our gravitational potential energy will increase. Likewise, we can see a relationship here with this equation. Our charge here in the middle, charge will be Q, and the distance A or B or anywhere else within this field is R, and we can calculate its voltage and potential energy from that. So now how do we relate the two of them? How do we relate electric fields and electric potentials? Well, the mathematical relationship between both can be given by the equation that we can see here. E equals negative delta V over D. E is the electric field strength, D is the distance that we are from the charge, and delta V is our electric potential. We can also rearrange that equation, as we can see here, to solve for the electric potential at a certain point, and we will just use a negative D, which is the distance from the charge, and an E, which is the field strength, and we can calculate our electric potential. So let's look at a couple examples of that so that it makes a little bit more sense. So in this example, we're going to say that our field strength is 10 volts per meter. So E is going to be equal to 10. And we're going to try to calculate the electric potential at point A here. So we're going to say that point A is 5 meters from this positive charge. So if we take A, 5 meters, and E, 10 volts per meter, 10 times 5, we'll get 50, and we know that it'll always be negative. So we have a negative 50 volts as our electric potential here at point A. Likewise, if we look here at point B, we'll say that point B is 2 meters from this positive charge. So D is now 2, E is still 10 volts per meter, D is 2 meters. So that at point B will be a negative 20 volts. So the electric potential at point B is a negative 20 volts. So what if we want to calculate the difference in electric potential between point A and point B? Well, we can take the electric potential at point B, subtract the electric potential at point A, and we can get that difference. So if we use those numbers that we calculated on the previous slide in our previous example, we'll take negative 20 which is our electric potential at point B, minus negative 50, which is our electric potential at point A, we'll get 30 volts. So 30 volts is the difference of potential energy between point A and B, or electric potential. So now we'll look at another example here that kind of brings all that we've talked about together again. Here we see we have a positively charged plate and a negatively charged plate. We see the field lines representing our electric field between the two plates. We see the lines going away from our positive charge and toward our negative charge, as we saw before. And now we're going to calculate electric potential of a charge that is in between those two plates here in the middle of that field. So here we have our equations again that we were already looking at. And we're going to say that our field strength here between the plates is known to be 100 volts per meter. Now we're going to say that this red positive charge is 8 meters away from this negatively charged plate. So what is this charge's electric potential then in this field? Well, we can just take this equation like we did before. We'll plug 100 volts per meter, which is our field strength for E, and 8, which is the distance that our charge is from this negatively charged plate. And when we calculate that out, we see that the electric potential at 8 meters is negative 800 volts. So what if that red positive charge moves to the right, and it's now 2 meters away from the negatively charged plate? Same thing, we plug 2 in for D, because it's now 2 meters away, and our field strength is 100 volts per meter. And we see that the new electric potential will be a negative 200 volts. So what would the difference in electric potential be? Well, we subtract A from B, and we see that we have a 600 volt difference in electric potential between 8 meters and 2 meters. So to review everything that we've talked about, electric fields exist around any charged object, whether it's positive or negative. And we use field lines to represent those electric fields. Any object within those fields will have an electric potential. That potential depends on the strength of the charge and the distance that you are from that charge. And we can represent that and connect the electric fields and electric potential with the equations that we see here. Again, E representing the electric field strength, D the distance from the charge, and negative delta V our voltage or electric potential. And we used it this way to calculate our electric potential.